Lesson: Machine Learning for Cloud Threat Detection. Machine learning has emerged as a pivotal tool in enhancing cloud threat detection, offering robust solutions to the ever-evolving landscape of cybersecurity threats. The integration of machine learning in cloud security is not just a trend, but a necessity due to the increasing volume and complexity of cyber threats targeting cloud environments. Machine learning algorithms can process vast amounts of data at a scale that humans cannot, identifying patterns and anomalies that suggest potential security threats. This lesson will delve into the practical application of machine learning for cloud threat detection, equipping professionals with actionable insights, practical tools, and frameworks to address real-world challenges effectively. The foundational advantage of machine learning in cloud threat detection lies in its ability to learn from data. Unlike traditional security measures that rely on predefined rules, machine learning models can adapt to new threats by analyzing historical data and identifying patterns indicative of malicious activity. For instance, supervised learning algorithms can be trained on labeled datasets containing examples of normal and malicious behaviors, enabling these models to classify unseen data accurately. Unsupervised learning, on the other hand, can detect anomalies without prior labeling, which is particularly useful for identifying novel threats that don't fit known patterns. A practical framework that professionals can utilize is the use of anomaly detection models, such as autoencoders and clustering algorithms like k-means. Autoencoders, a type of neural network, can learn a compressed representation of input data and then reconstruct it. If an input deviates significantly from the learned representation, it's flagged as an anomaly. This approach can be particularly effective in detecting unusual network traffic that might indicate a breach. Clustering algorithms like k-means can group similar data points, and any data point that doesn't fit well into an existing cluster could signal an anomaly. Incorporating these models into cloud environments can be achieved using platforms like Amazon Web Services and Microsoft Azure, which offer machine learning services tailored for security applications. AWS's Amazon Guard Duty, for example, leverages machine learning to analyze billions of events across AWS accounts, detecting threats such as compromised instances and unauthorized access attempts. Similarly, Microsoft Azure's Security Center uses machine learning to identify and respond to threats in real time by analyzing network traffic and access patterns. To implement machine learning-based threat detection, one practical approach is to utilize TensorFlow, an open-source machine learning framework, alongside cloud-based services. A step-by-step application might involve collecting network traffic data, pre-processing it to ensure quality and consistency, and then feeding it into a TensorFlow-based model to train and evaluate its performance. Once the model is trained, it can be deployed in a cloud environment to monitor real-time data and flag any anomalies that suggest a security threat. This method not only enhances detection capabilities, but also scales efficiently with the increasing data volumes typical of cloud services. The effectiveness of machine learning in cloud threat detection can be illustrated through case studies. For instance, Netflix employs machine learning to detect anomalous account activity, protecting its vast user base from potential security breaches. By analyzing login patterns and device usage, Netflix can identify suspicious activities that deviate from a user's typical behavior, thus preventing account hijacking and unauthorized access. This proactive approach not only safeguards user data, but also preserves the company's reputation and trust. Despite the obvious advantages, there are challenges associated with the implementation of machine learning for cloud threat detection. One significant hurdle is the potential for false positives, where legitimate activities are incorrectly flagged as threats. This can lead to unnecessary alerts and investigations, diverting resources from genuine security incidents. To mitigate this, it is crucial to fine-tune machine learning models continuously, incorporating feedback from security analysts to improve accuracy. Furthermore, combining machine learning with other security measures, such as rule-based systems, can enhance overall detection capabilities and reduce the likelihood of false positives. Another challenge is the need for high-quality, labeled data for training supervised machine learning models. This data scarcity can be addressed by employing techniques such as data augmentation and transfer learning. Data augmentation involves creating additional training examples by modifying existing ones, thus enriching the dataset without requiring new data collection. Transfer learning, on the other hand, leverages pre-trained models on similar tasks, adapting them to the specific context of cloud threat detection. These techniques not only optimize the training process, but also improve the model's ability to generalize to new, unseen threats. In terms of practical tools, the use of open-source platforms like Apache Kafka for real-time data streaming can significantly enhance the capabilities of machine learning models in cloud threat detection. Kafka can handle high-throughput data streams, allowing for the continuous monitoring of network traffic and user activities. By integrating Kafka with machine learning models, security teams can achieve real-time threat detection and response, ensuring that potential threats are addressed promptly before they escalate into significant breaches. Statistics highlight the growing importance of machine learning in cybersecurity. According to a report by Cybersecurity Ventures, cybercrime is predicted to inflict damages totaling $6 trillion annually by 2021, underscoring the critical need for advanced security measures. Machine learning offers a scalable and effective solution to this challenge, enabling organizations to stay ahead of sophisticated cyber threats and protect sensitive data and systems. As machine learning continues to evolve, its application in cloud threat detection will likely expand, incorporating more advanced techniques such as deep learning and reinforcement learning. These approaches can further enhance detection capabilities by modeling complex patterns and behaviors that traditional methods might miss. However, the successful deployment of these technologies will require ongoing investment in research and development, as well as collaboration between cybersecurity experts and data scientists to ensure that models are both accurate and interpretable. In conclusion, machine learning has revolutionized cloud threat detection by providing powerful tools and frameworks that can identify and mitigate threats more effectively than traditional methods. By leveraging platforms like AWS and Azure and utilizing frameworks such as TensorFlow, professionals can implement scalable and efficient machine learning models to protect cloud environments. While challenges such as false positives and data scarcity exist, they can be overcome through continuous model refinement and the use of techniques like data augmentation and transfer learning. As the threat landscape continues to evolve, machine learning will play an increasingly vital role in safeguarding cloud infrastructures against cyber threats, ultimately ensuring the security and integrity of digital assets.